So today we would like to look at theoretical approaches to understand the fractional quantum Hall effect. This problem is simple to formulate. We know what the Hamiltonian is. Here, it's written here. It has a kinetic term where all the electrons interact with the magnetic field. It has an interaction term where the electrons interact pairwise. And it has a disorder term where the electrons interact with a disorder potential. We'd like to, in principle, in our dreams, we would like to solve Schrödinger's equation for this Hamiltonian and get the wave functions, get the spectrum, calculate response functions, everything. In practice, we'll do much less than that. But it should be said that the answer to this is known to us, and it's known to us from experiment. We know from experiments that there are fractional quantum Hall states where the Hall resistivity is quantized, and the longitudinal resistivity vanishes. This is the fractional quantum Hall effect, and we know it happens at a particular set of filling fractions. We know, for example, for nu equals 1/3 and 2/5 and others, we get a fractional quantum Hall. And for other filling fractions, like 1/2, we don't. We never get a fractional quantum Hall. We know that when there is a fractional quantum Hall, there is also an energy gap between the ground state and the set of excitations, while at nu equals 1/2, there is no such energy gap. So that is what the experiment is telling us. So what do we still have to do? So of course, there's a lot to be done. There's a very long list of questions we would like to be able to answer. For example, we would like to know why at 1/3 we have an energy gap and at 1/2 we don't. What determines the filling factors where an energy gap opens? Why does it open at all? We know that when there are fractional quantum Hall states, there are fractional charges as excitations. We would like to know how they develop microscopically. What properties do they have? We'd like to know, to analyze the edge structure. We'd like to have a way to calculate the magnitude of the energy gap. How it depends on the type of interaction between electrons. We'd like to be able to calculate response function. There's a very long list of questions I did not even write here. Effect of disorder, and so on and so forth. We have a long list of questions. How are we going to solve them? So, naively, the first thing you think about as a theoretical physicist is to apply the wonderful idea of perturbation theory. Let's find a problem that's close to our problem, and we know to solve exactly, and then do perturbation theory. And the first naive idea is let's neglect electron-electron interaction, solve the problem of non-interacting electrons, and treat electron-electron interaction perturbatively. That's not going to work. And the reason it's not going to work is that if you neglect electron-electron interaction, the ground state of a partially filled Landau level becomes highly degenerate. And applying the procedure of first-order degenerate perturbation theory becomes very, very difficult. Let's see that. Here we have a sketch of a Landau level with 12 states. 4, 5, 6, 7, 8, 9, 10, 11, 12. And we fill 4 of them. So, and it doesn't matter energetically, in terms of the kinetic energy, which 4 of the 12 we are filling. There are 12 choose 4 possibilities. And we need to diagonalize electron-electron interaction within a subspace of the degenerate ground states of this dimension. This is not such a big dimension, but imagine that we had 1 billion electrons, and we would have to choose 1/3 of a billion out of 1 billion. How many possibilities we would have? That would be an enormously large subspace of ground states, and diagonalizing electron-electron interaction in that subspace is hopeless. So we need a different approach. We need a different set of approaches. Before looking at those, let's identify the dimensionless parameters in this problem. And there are 2 of them. In fact, there's a third one. You notice that I neglected here the disorder part of the Hamiltonian. It's hard enough even without it. So we have 2 dimensionless parameters. One is the ratio of the 2 energy scales in the problem. the Coulomb energy scale divided by the kinetic energy scale. And the other one is the filling fraction. Both are dimensionless. This ratio is typically small compared to 1, not very, very small, but reasonably small compared to 1. The filling fraction is just a fraction. As we already explained here, if the filling fraction is a fraction, taking this parameter to 0 is not going to help us. So we need a different approach. We're going to talk about 4 types of approaches, 2 today in this video, a third one in a different video, and a fourth one in a set of videos, because we'll get into details. So today we'll talk about the idea of guessing a wave function or having a trial wave function, and the technique of using a numerical work. In the next segment, we'll talk about wire constructions, where we think about the plane as being made of a series of lines, and we'll talk about the idea of flux attachment, and we'll do that getting into some details. So let's start with the idea of Laughlin's wave function. Before we even introduce this one, let me emphasize what a mind-boggling idea this is. We're trying to have a trial wave function for a many-body system with lots and lots of electrons with interaction, and we're trying to guess not only the ground state but even excitations. So let's see how this happens. To start with, what we'd like to look at is the Laughlin wave function for nu equals 1/3. But to start with, let's first look at nu equals 1. That's definitely easier. Not only that, let's look first at the single particle states within the lowest Landau level. Those will form, at the end of the day, both the nu equals 1 and the nu equals 1/3. So for a lowest Landau level, we saw in a different video how the wave functions look in the Landau gauge. Here we're using a different gauge, the symmetric gauge, where the magnetic field is, or the vector potential is 1/2 B cos R. You saw it in the Hamiltonian a couple of slides ago. And the wave functions for the lowest Landau level in this gauge are given here. They're a product of z to the power m multiplied by a Gaussian factor. And m here is a quantum number that defines or that characterizes each of the single particle states. Now it has a clear physical meaning. It's an angular momentum on top of everything, but it has a clear physical meaning. If you look at the absolute value of the wave function squared, for these wave functions for m equals 1, for m equals 4, for m equals 7, and for m equals 10, you see, first of all, that the larger m is, the farther the wave function is from some origin. So this is the wave function squared as a function of a distance from an arbitrarily chosen origin. So the farther m is, the higher the m is, the farther the wave function squared is from the origin. Which means this is, the m equals 0, this is the m equals 1, this is the m equals 4, this is the m equals 7, and so on and so forth. And what we are going to do now is we're going to look at the nu equals 1 state by filling those states one by one. It's going to be a wave function for many, many electrons, n electrons, filling all those states one by one, creating a system where we are going to have a density of electron that's uniform and corresponds to 1 electron per flux quantum, which is nu equals 1, but only over a certain range of the plane. We're not going to put the system on periodic boundary conditions or hard-wall boundary conditions. This is too difficult. We're also not going to look at an infinite plane because we're writing a wave function in first quantization. It must have a finite number of degrees of freedom. So to create a droplet of a nu equals 1 state, we're going to fill all the angular momentum states m going from 0 to some capital N, and we'll get a state where we filled a certain range of single particle states. Now, the wave function for those states is going to be just the Slater determinant, right? Those are fermions and that's how we anti-symmetrize the wave function. And what we get in this particular case is that the Slater determinant is nothing but the van der Moon determinant, which we know for math will have this form. It will be a product of all pairs of electrons of Zi minus Zj multiplied by a Gaussian factor. Now, there are two things to be said about this van der Moon form of the wave function. First, and not surprisingly, the wave function makes sure that two electrons do not get to the same point, that the wave function vanishes if two coordinates are the same. This is what Slater determinants are paid for, right? Second, what you see here is a polynomial in each of the coordinates Zi. And if you look at it and open the brackets, you find that the highest power in this polynomial is n, which means that the size of the droplet is of the order of n times the magnetic length squared. So we have for this size of area, we have a droplet of nu equals 1. One more thing we can say about this nu equals 1 wave function is that if we insert a flux tube at the center of this area and turn on flux inside this tube and change it from 0 to 1 flux quantum, what will happen to the wave function is that each electron that had an angular momentum m will be transferred to m plus 1, which is the same as saying that the wave function, the original wave function, will be multiplied by this factor, a product of all the Zi's of all the set of electrons. And then we'll get this wave function in which simply m changed into m plus 1, leaving the m equals 0 unoccupied, making a hole with a charge of 1 electron. So this is nu equals 1. And now let's shift to nu equals 1/3. And let's look at Laughlin's trial wave function for nu equals 1/3. So here it is. It is only 1 digit of difference from the nu equals 1 wave function that we looked at. And this is this digit. Instead of Zi minus Zj to a first power, we have for each pair of electrons Zi minus Zj to a power of 3. That means that the highest power in the polynomial is now not n, but 3n. Which means the size of the droplet is not n LH squared, but 3n LH squared. The droplet went bigger by a factor of 3. The magnetic field did not change at all. It's the same magnetic length on both sides. So instead of having nu equals 1, we now have nu equals 1/3. We have a droplet of nu equals 1/3. The wave function still vanishes when two electrons get to the same point. But now it vanishes much more strongly. It vanishes, the wave function vanishes to a power 3. The wave function up to the very squared vanishes to a 6th power. So we have a wave function that describes nu equals 1/3, that keeps electrons away from one another, and by that probably minimizes their interaction energy. And it's a wave function that we can try and look at and check. And first thing we'll do is, as we did for nu equals 1, what happens if we insert a flux quantum at the center of the droplet and shift each m to m plus 1? Well, we just change the size of the droplet by 1 unit of angular momentum, which corresponds in nu equals 1/3 to 1/3 of an electron charge. So this operator now creates a quasi-hole not of 1 electron charge, but 1/3 of an electron charge, which is what we know should be the case for nu equals 1/3, as we saw in an earlier video. So now we have a wave function for nu equals 1/3, a trial wave function, and we have a wave function for a quasi-hole. We should still somehow develop confidence that this is a wave function worth looking at. But before doing that, let's believe in it and watch one consequence that comes out of it that is pretty interesting. And this is a consequence that comes out of looking at the wave function for the quasi-hole. you know, quasi-holes are excitations, and they have various properties, a mass, a charge, and so on. One property, which is the one I'd like to focus on, is the property of quantum statistics. So what do we know about quantum statistics? We know there are fermions and bosons. We know it's a world of difference. And one reason why it's a world of difference is when it comes out at you when you look at the statistical mechanics. Statistical mechanics of fermions is very, very different from that of bosons. This is why fermions form metals and bosons form Bose-Einstein condensates. And all this difference comes out of what happens to the wave function as you interchange two coordinates. Now here we have a wave function that's slightly different. The wave function is a function of, and the Hamiltonian also, is the degrees of freedom in the problem are the electronic degrees of freedom. Now we insert into this system that's made of electrons, we install in it quasi-holes. And the way we do that, we take the system, and as we said before, we put in two flux tubes, and we turn the flux on in each of the two flux tubes from 0 to 1 flux quantum. So now we have the positions of the flux tubes as parameters in the Hamiltonian and in the wave function. They are not dynamical degrees of freedom at the discussion that we're having now. Now we'll define the statistics in the following way. We'll define it by saying, suppose that we take those two quasi-holes and interchange their positions adiabatically, starting from the system in the ground state and going all the way with the system staying in the ground state. We can do that. It's a gap system. There's an energy gap. It's 1/3. Nu equals 1/3. So suppose that we do that. What geometric phase does the system acquire? And you won't be surprised to know that if we do that for nu equals 1, we will get a geometric phase of pi, which is what we expect from two fermions. But what will we get if we do this exercise for nu equals 1/3? In fact, we'll simplify this exercise by taking one quasi-particle and circling it around the other, leaving the other one at rest. This is the same as two interchanges, or as doing the interchange twice. So we can divide by 2 at the end. The geometric phase, you know, in order to get the geometric phase, we need to look at the scalar product of the ground state for a position, for a particular position, R1 and R2 of the quasi-holes, sandwiched with the gradient of the same wave function with respect to these two parameters, with respect to the trajectory that these two parameters take, and integrate over the trajectory. In fact, we'll do something that's slightly simpler as a first exercise. We'll take our system, and instead of putting two quasi-holes, we'll put just one, and we'll take this one quasi-hole and move it around in a circle and calculate what's the geometric phase that the system accumulates as a single quasi-hole goes around a closed trajectory. The wave function we already talked about for a quasi-hole, and here's the position of the quasi-hole before we put it at the origin, but now we'd like to have this as a parameter. We'll calculate the geometric phase after normalizing this wave function, and we'll see what the geometric phase is. And when you do that, I won't do this calculation here, but when you do that, what you find is the following. You find that the geometric phase is 2 pi multiplied by an integral over this area of the density. Another way of saying it, it's 2 pi times the number of electrons that this quasi-hole went around. Now that we see that, now we can see what's going to happen if we add here another quasi-hole and let the first one go around it. Adding a quasi-hole here changes the number of electrons in the loop by 1/3, because a quasi-hole has a charge of 1/3. I'm not putting too much attention on signs here. So we change the number of electrons by minus 1/3 if you want. Which means that the value of this integral will change by an extra phase of 2 pi over 3. which means as one quasi-hole goes around another, it knows about the presence of the second one by the geometric phase it accumulates, having a factor of 2 pi over 3 relative to what would have happened if this quasi-hole was not there. So we did not get the phase factor that we would expect from fermions. We did not get the phase factor that we would expect from bosons. By this definition of the term quantum statistics, we found a different type of statistics. And this is what gave this type of particles the name anyons. They are not fermions, they are not bosons. They can take any statistics. We did here nu equals 1/3 and we got 2 pi over 3. For different fractional quantum Hall states, we will get different values, and we will see that later on. So quasi-holes and quasi-particles as well in the fractional quantum Hall effect are anyons. They can have any quantum statistics with respect to one another, in contrast to what we know from fundamental quantum mechanics. Now, we can ask, what consequences does this have? Will it have the same outcomes, important outcomes, as the fermionic and bosonic statistics have on the statistical mechanics of systems? If not, how can we observe this type of statistics and so on? Those are very important questions. I will not get into details now. What I'd like to say now in summary about this description of the trial wave function, Laughlin's wave function approach to understand the fractional quantum Hall effect, what I'd like to say are several reasons why we believe in the Laughlin wave function as a good description of nu equals 1/3. First, you can write down the Laughlin wave function. You can calculate numerically by exactly diagonalizing the ground state of a nu equals 1/3 state for a small system. And you can look at the overlap of these two wave functions. And for a small number of electrons, this overlap is remarkably high. It's very close to 1. Now, of course, as you make the number of electrons larger and larger, the overlap will necessarily die out. Because, for an infinite system, the Hilbert space is too large for you to guess what's the ground state wave function. But for a small number of electrons, the overlap is remarkably high. Second, we can write down an Hamiltonian of electrons in a lowest Landau level with some type of interaction. That's not a Coulomb interaction. It's not a realistic interaction, but some kind of interaction. We can write this type of Hamiltonian for which the Laughlin wave function is the exact ground state, and the quasi-hole is an exact excitation. And that Hamiltonian is not that far from the Coulomb one. So this approach gets the topological properties right. It gets the charge of the quasi-hole right. It gets also the statistics that correspond with the statistic that we calculate with the other approaches. And it gives us a tool to estimate the energy gap. So this is a trial wave function for nu equals 1/3. There's a whole set of trial wave functions for other fractional quantum Hall states. The Jane functions, and various other examples that we will get to. I will not get into them now because we'll talk about them in other segments. What I do want to talk about now, very briefly, is the way we can use numerical techniques, numerical tools, to analyze fractional quantum Hall states. So we would have liked to diagonalize exactly the Hamiltonian for many, many electrons. We cannot do that because the Hilbert space is exponentially large. But for a small number of particles, we can. And for small systems, we can extract the spectrum of excitations and the energy of the ground state. We can compare to trial wave functions, as we talked about. And we can also carry out two types of calculations which we are not talking about here. One is to identify whether a particular wave function describes the ground state of a gapped Hamiltonian or a gapless Hamiltonian. And we do that by looking at correlators, equal time correlators of various local operators within the ground state that we examine. And we can look at topological properties through calculations of the entanglement spectrum. Those would require too long a time, so I'm not getting into them. So I will now just give you a quick look at two examples of numerical works to look at fractional quantum Hall systems. So in the first example, we see a calculation of the overlap of two wave functions, the exact wave function obtained numerically with a trial wave function. The overlap is of course calculated numerically, and it is plotted here as a function of a parameter in the system. This particular system is a bilayer quantum Hall system, and the parameter that we vary is the distance between layers which are coupled to one another. Now, as we see here, for large distances, this overlap is very, very close to 1. So the trial wave function is a very good guess to the exact one. For small distances, the overlap is not good, is not close to 1, and apparently there is some phase transition between large distances between the layers and small distances, which we see here in the numerical calculation. In the second example, we see calculation of the exact spectrum of excitations of a finite system, of course, here for a filling factor of 3/8, and this spectrum, this calculated spectrum, is compared with spectrum obtained from trial wave function approach. And we see that the agreements between the exact energies of the excitations and those obtained from the trial wave functions are pretty good for the low energies. So to summarize, what we did today was to look at two approaches to study the fractional quantum Hall effect, two theoretical approaches. We looked at trial wave functions, and we looked briefly into the world of numerical calculations. Next time, we will look at coupled wire constructions, and after that, we will look at flux attachment.